All right. So thank you very much, everybody, for attending and being patient with us as we work through connectivity problems. But today I'd like to introduce Dr. Hanna Sizemore, who is going to be telling us all about an exciting topic that we've all been thinking about for a while now, which is perseverance and how the little rover is holding up. So thank you very much, Hanna, and take it away.
Thanks, Jesse. Well, hi, everyone. Long time no see for some of you. And I'm sorry that I have not had the chance to meet a lot of you yet, including Jesse, until today. But hopefully we're on the path to being back in the building and seeing each other soon. Jesse had reached out to me a few months ago because apparently there's been a lot of interest in hearing about perseverance since the landing. Sorry it's taken me so long to get around to actually making this available for you. And I'm having a little problem with the display. Okay. So what I've done here is I've tried to put together a pretty not too technical, very accessible talk. The first half will just talk about the mission itself. And then the second half will be my links to it. I'm not a member of the science team on this mission, but my former PhD advisor is, and I have other collaborators on the mission. So the second half of the talk will be about climate modeling that we're doing to inform some of the mission observations. Now, I'd really encourage you, if you can, even remotely, to shout out questions or raise your hand, because I do want to kind of tailor this as we go to what you're most interested in. All right, so Perseverance landed on February 18th, 2021, after taking off in July of 2020. It was the fourth landed mission that we've actually been able to photograph the descent from orbit with a high-rise camera. The very first mission that we were able to do this with was my first mission, the Phoenix mission in 2008. So what you're looking at here in the background is Jezero crater. The small circle is the landing site where the spacecraft eventually came to rest, and the square inset is, of course, the spacecraft hanging from the parachute. And here's another high-rise image of Jezero crater, and I think you can probably tell just at a glance why this was a high-priority target. What you're looking at here on the left is a large sinuous river channel breaking through the wall of the crater, extending to a large delta in what was once a crater lake about the size of Lake Tahoe. We think that a lot of this water activity was going on about 3.5 billion years ago. And so we have preserved here sediments from the time when Mars was probably most habitable. So the mission itself is very much geared toward astrobiology. And there are these four themes that you see in a lot of the large Mars missions: geology, astrobiology, pure samples, and then preparation for human landing. So on the geology side, what's really trying to be done is trying to study the rocks and the landscape to understand
Hanna, can you still hear us? You seem to have frozen out.
I'm still here.
Okay,
No,
great. We can hear you again.
I'm sorry. It may just be the weather. Did you guys hear me saying that our goal was to understand the periods of wet and dry?
We did just now, so
Okay.
there.
All right, so the big focus is understanding the geology and understanding these ancient periods of warm, wet climate, and how the sediments from those periods are interleaved with dry periods when you have mostly sediments from the air, aeolian deposits, and volcanics. And the spacecraft is designed to assess that past habitability, the environmental conditions, but also to look directly for biosignatures, chemicals and physical structures in the rocks that can tell us that organisms were once there. And if it's not able to actually find biosignatures, it's also supposed to identify rocks that would be great at preserving biosignatures so that we can save them and bring them back to Earth eventually and analyze them here. And like any Mars high budget flagship class mission, there's a lot of technology demonstrations on this spacecraft and efforts to prepare for human landing through in situ resource utilization. So using what you have on Mars to make the things you need to survive and the rocket fuel you need to come home. All right, so this is just a geologic map, simplified, basically showing you some of this complexity of the mixture of ancient wet sediments in the delta and the lake shore and the river channel coming in, and how those are intermixed spatially with ash and airfall deposits and dunes and things like that. The yellow line in this image is showing one possible pathway for the spacecraft to traverse the delta and the crater wall. The goal here is to move from lake floor materials to delta materials, which are probably the best for preserving any potential biota from the past. And then up to the lake shore, another good place to look for chemical markers, and then eventually to the crater rim where there may have been hot springs, another excellent place for biology. And here's a look at the rover itself. This is a very large, heavily equipped rover. It's about the size of an SUV. It carries directly on from the Curiosity rover, but it has a larger robotic arm and more sophisticated instrumentation. Now, the most important instruments for the astrobiology mission here are probably the ones I'm least qualified to talk about. And those are the Sherlock ultraviolet spectrometer, the Pixel X-ray spectrometer, both of those on the robotic arm with the drill and the sample collecting apparatus. And then the SuperCam, which is a whole package of spectrometers used to look at vaporized rock that we blast off with laser. Now, right now, I can't speak to a lot of that in detail if you have questions, but as the mission progresses and I'm going to conferences, there's going to be a lot of talk, and I'll get my head around all the different parts of the spectrum, all these different techniques and how they link to habitability, and I'll be happy to answer those questions when we're all back in the building and you can knock on my door. For right now, I'm most involved with Rimfax, Mastcam, which is just like the standard picture taking cameras, and the weather station. And particularly my link to the mission comes through Rimfax, which is the subsurface radar. My former PhD advisor, Mike Mellon, helped design, propose, and build this instrument, and will be directing a lot of the observations as part of the science team throughout the active mission. Now, in addition to the cameras and Rimfax, we also have MOXIE. That is the ISRU instrument. And basically what it does is it takes carbon dioxide from the atmosphere and produces pure O2 for human consumption or for propellant. It's the first time we've ever had an ISRU demonstration on another planet, although people have been working on building these things on Earth for a long time. It's the first one that's flown, and it's already been successfully tested on Mars. Since this is the instrument most linked to my work and probably the most interesting to a radio astronomy audience, we'll talk a little bit about Rimfax. This is a low power sounding radar, 5 to 10 watts. The frequency range is 150 megahertz to 1.2 gigahertz. It basically has a nadir pointing antenna that hangs behind the rover, and you're seeing a picture here of it being tested on a sled in Norway, where it was developed. Its name comes from Norse mythology for the horse that brings the night. But of course, because it's a NASA mission, they force an acronym into this, which I can't remember because it's too complicated. But they made it happen. Now, we hope that this will actually show us geological interfaces down possibly tens of meters, at least 10 meters, and be able to resolve structures, vertical structures in the 15 to 30 centimeter thickness range. However, doing radar in a planetary subsurface is a bit different. The kinds of radar you guys are used to, instead of propagating through vacuum, the signal here has to propagate through materials. And what we're interested in is finding out what materials are down there and how far away they are from the surface. And there are important ambiguities in that because the dielectric constant controls the power dissipation and the speed with which the signal travels. So we're always playing games to try to get out of the redundancies here. Basically, the subsurface we know is going to be a mixture of ice, air, and rock. We don't know the exact proportions, and we don't know the exact depths to the locations where we'll eventually observe dielectric interfaces that cause a radar reflection. So we have to think very carefully about designing laboratory experiments to nail down the dielectric properties of these materials in advance, and then design our observations so that we have some controls on the geometry. Happy to answer some questions about that later on if you have them. So moving on from the science instruments, there are a lot of technology demonstrations on this spacecraft. We already talked about MOXIE, which is the oxygen production experiment. The one that has got a lot of attention, of course, is the Ingenuity helicopter. So the first time we've had powered flight on another planet, and it's particularly challenging on Mars because of the extraordinarily thin atmosphere. So we're sitting in about 1 bar of atmosphere right now on Earth. Ingenuity is flying around in 6 to 10 millibars of atmosphere, probably closer to 10 at their elevation, and it's a real challenge. So the blades on this little drone are about this big. Can anyone, I hope you guys can see what I'm doing. I'm giving a distance about half again as wide as my shoulders. And we really can't put much payload on this thing at all, just a very small camera. They are able to get video from the rover. And I'm playing here the very first flight back in April. Since then, there have been 7, at least, successful test flights completed. The nominal mission for Ingenuity has been completed and all tests passed with flying colors. They're now on an extended mission since they've proven that the helicopter can fly, maneuver, get back to where it needs to be, and survive some safety faults. It will now be used to help plot the safest route up that delta and crater wall as the mission goes on. From a scientist's perspective, this is a lot of money for not a lot of science, and there's been plenty grumbling on the science side about this, but I've gotten so much enthusiasm, so many excited questions from everybody from my optometrist to my dentist about this. So I think probably NASA did do a good thing here. If you want to know more about the really cool technology demonstrations, I've put the link up here on the screen where you can learn about the wheel improvements, the microphone, the sample collection mechanism, the aero shields. Like, there's a lot of cool new stuff on the spacecraft. So one of the reasons that this mission is flying now, and why it has so many of these tech demonstrations on it, is it's part of a much larger effort to bring Martian materials back to Earth. And this was an effort that was prioritized in our last decadal survey back in 2013. And it's eventually going to be a joint effort between NASA and ESA that spans 2 decades. So we're in the first phase now, which is the Perseverance rover being sent primarily by NASA, but with a lot of European participation to actually find and collect samples. Basically put them in little cylinders, drop them out on the surface. Then in approximately 2026, there'll be a large ESA mission that will send a fetch rover there to pick them up, a Mars ascent vehicle there to launch them back into orbit, and then a large orbiter to bring them back to Earth. ideally to return them to North America sometime in the early 2030s. And then there would be, following this, a large special Earth-based laboratory where they would be processed. And the resources in that laboratory would be expensive at the order of another major mission. Now, the details of this are changing a lot. I've seen it presented a few different ways at conferences over the last 2 years, and I'm sure there's still a lot to be hammered out. But it is happening, and the story and the mission architecture are kind of settling now. The BBC actually has a really nice illustrated summary of this if you're interested and want to kind of see some of the neat things they do with launching the materials back to orbit, gravitating them with the orbiter and things like that. Okay, so where do I come into all of this? I'm an ice and climate person for basically my whole career. I got started as a PhD student doing landing site selection for the Phoenix mission, predicting where we would find ice, how deep we would have to dig to get it, things like that, and have continued in that vein since. For the past few years, I've been really heavily involved in an effort to make global maps of ice in the Martian subsurface, with the goal of selecting human landing sites and using that ice as a resource to produce propellant to come back with a human mission. So what you're looking at here is one of the maps that came out of that effort, which is called SWIM, or subsurface water ice mapping. Don't worry too much about what CI and the numbers mean, but basically bluer means more ice, paler blue means less ice, gray means we don't know. And the little crosses are locations where we have something like approximate ground truth. Is there ice in the ground there or not? Because they're impact craters that have formed while we were watching an exposed bright ice. We only have one place with real ground truth where we know that there's buried ice on Mars, and that's at the Phoenix landing site, which is near 70 degrees north above the latitude range in this map. You can see Perseverance here as a star, and it's very far from anywhere that we're confident that there's ice, but nonetheless, we're still going to look. Now, there are some big challenges to finding buried ice on Mars. Number one thing being that our spacecraft fleet and available instruments are not ideally designed for this, this effort. We basically have instruments, thermal spectrometers, neutron spectrometers that are really good at looking for ice in the top 1 meter to 50 centimeters. And we have sounding radars in orbit that are really good at looking for ice at depths of several tens of meters or kilometers. But we have this gap in our ability to look for ice between about 1 meter and about 20 meters. And unfortunately, at the places where you would like to send humans and spacecraft, the nice warm places, if there's ice, we expect that ice to be in that depth range that we can't see. So that is really pushing NASA to do another orbital mission, but it's also really important to milk all the ground truth we can out of landed instruments. So Perseverance is the first Mars lander that's GPR equipped, and Tianwen, the Chinese lander with the Zhurong rover, is the second. So this year, suddenly, we have an opportunity to look for ice at locations other than the Phoenix landing site and the Viking 2 landing site. Now, here I'm showing a map of everything that has landed successfully so far, plus ExoMars, which is coming next year. Phoenix is the only site we know 100% for sure. We went there, we dug up ice, it was there. Viking 2, we're quite confident it's there, and the hole was not dug deep enough to get to it. There won't be any real digging going on at Perseverance, but we've done a lot of modeling to look at where we want to aim the radar and what images we want to take to try to understand ice there. So this slide is just showing the very basics of how we do this modeling, how we predict where ice ought to be. We're getting late on time because of our late start, so I'm just going to say basically this. The image that you're seeing on the right is taken in Antarctica, and it shows what we expect on many locations on Mars. You've got a dry layer of soil, and below that, with a sharp boundary, there's hard ice cemented soil or pure ice. And we can predict where that will occur because we know there's water vapor in the atmosphere. We can predict the temperatures in the subsurface. any place where the temperatures are cold enough and the saturation vapor density is low enough, below that of the atmosphere, water vapor from the atmosphere will diffuse in, freeze out, make ice. Anytime the dirt is too warm, that process will run in reverse. Ice will sublimate away. So we can use that basic physics to predict where ice ought to be, even at the locations where we can't look yet. And so that's what Mike Mellon, the Rimfax co-I, who I'm working with, has been doing. And I've been helping out mostly in trying to figure out how to get that atmospheric boundary condition right. What you're looking at here is a history of how deeply ice was buried at 5 landing sites for the last 2.5 million years. And in black, you can see the Phoenix landing site, which is basically, there's been shallow ice there for a very long time. The exact depth wobbles a bit, but you can go there and dig up ice anytime you want. All the other landing sites in this plot are basically, most of the time the soil is desiccated, completely dry, but periodically, as the tilt of Mars's axis wobbles, you get conditions right where you can build ice in the soil. And this happens every couple of 100,000 years and persists for tens of thousands of years. So you can actually build up ice. So Perseverance is not a great site for this. It's generally too warm, too dry, but you do have episodes. One of them is around 500,000 years ago. There is a chance that we preserved ice from that time. The Zerong landing site is actually substantially more favorable for populating the soil with ice, and we'll be finding it now. Okay, so there's more to actually making decisions about how to point the radar and analyze the results than just looking at the general condition in the crater. The soil conditions on the ground are going to be very important. And what you're seeing here is the same plot from the previous page or previous slide, but now we're looking just at the Perseverance site and how deep the ice is over the past 2.5 million years for different types of soil. So we have this parameter called thermal inertia, which basically tells us how good the soil is at holding heat, and it's a proxy for what the grain size of the texture of the soil is. So 50 SI units of thermal inertia is very powdery dust, not safe for your rover. It's what killed Spirit. You don't want to drive in this stuff. 315 is a nice safe sand. And you can see that rover safety and depth of ice and time to deposit ice are completely anti-correlated. So basically the best places to look for ice in terms of soil type are the places you don't really want to drive your rover, even though it's bigger and more capable than MER. There's a similar story going on with slopes. Here you're seeing a table from a paper that Mike and I just submitted on Monday, I guess, looking at ice availability and depth in the current climate at Jezero for a variety of soil types. Again, that thermal inertia 50 to 315 and different albedos, brightnesses of the soil and different slopes. Basically what we're finding is in order to have ice there right now and shallow, we need to be on slopes that aren't safe for the rover, near the angle of repose where sand would actually start to spill downhill of its own accord. So that's a little bit grim, but it does lead us into making some smart choices from the beginning. So what's new here is that we've developed a totally different or new treatment of the atmospheric humidity boundary condition, but we've also computed depths and survival times of the ice during these most recent high obliquity excursions. So now we can be smart. We will know when we have an opportunity to be doing GPR sounding at locations where ice could have been there 500,000 years ago. We'll also know precisely where to do imaging of slopes to look for surface signs of ice in morphology. And we're going to have weather stations that can be used to validate our treatment of the atmosphere. And of course, our model predictions are not only relevant to Jezero, they're relevant to Zerong, ExoMars, and to future landing site selection, and will tie into a new mission that we hope will be going in a few years, Ice Mapper. Okay, so I think I'm running slightly over at this point. I'll sum up. Basically, Mars is getting really crowded. It's a really exciting time to be a Martian scientist. We're sending so many spacecraft, really starting to drill down on some of the core questions that we've been asking for the last 50 years. The key drivers for perseverance are really not in my main wheelhouse. You know, they're geology, mineralogy, astrobiology, and these tech demonstrations. But there's so much going on with this mission. There's plenty of room for ice and climate folks like me to capitalize on it. And I think this is part of a real ladder that's being built now to understand ice resources and human landing. So I'll stop there and take any questions.
Awesome. Thank you so much, Hannah. Yeah, so if people have questions, and feel free to unmute themselves. And Hannah, if you still have more things you want to discuss, if we still have time, by all means do so. Well, since nobody is jumping right away, I would like to start things off by asking a question, if you are willing. Can you go into a little bit more depth with Rimfax? If it is not too utterly complicated, can you explain how you're able, what data you actually receive and how you're able to interpret it in that triangular plot of materials? What is that actually?
Okay. And I apologize, I should have thrown an extra slide in here, which I may Google for right now. Hold on just a second. I'm going to show you something. What we get back is a Radargram, which so this is what we're looking at here is, if I can pull this over. These are from Sherrod, which is an orbital radar. So what's happening with Sherrod and with Rimfax is you're moving laterally while pinging the surface at intervals. And you get back this track of reflections, which can show you layers in the subsurface, which is any place that you have a dielectric constant sharp enough, a contrast sharp enough that you get a lot of the power sent back from that interface. So Sherrod, which we're looking at right now, is kind of operating over many kilometers laterally and many tens of meters vertically. And our job is to figure out how deep those reflectors are, and as best we can, what the material is on the two sides of them. It will be the same game with Rimfax at a different scale. So we will be seeing these radargrams, these slices through the subsurface with the layering. And our job will be to figure out what interfaces are those reflections coming from, what are the materials on either side, and how deep are those interfaces.
Okay, and you said you had a slide. I don't know if you're able to find it, but we can't see it here.
Oh, can you guys not see the radargram display with an A, B?
No, we're
We can
just
only see
seeing
the first monitor, Hannah. You might need to drag it to the other monitor.
Oh, yep. Sorry, actually, can I just switch my screen share?
That should be pretty quick. Yeah. We're still looking at the PowerPoint. Ah, no.
I'm not sure, like, I literally have we'll fix this. Literally have it overlapping in my view, but I'm fixing it. Do you have it now?
No, yes, here it comes.
Okay, so
Yeah,
what
we're
you're looking at here, A is just the radargram. B is the radargram with depth correction, considering what the dielectric constants of materials probably are, and some known geometric constraints. And then C is showing you the track of the radar above the surface.
Okay. And so each of those horizontal features, effectively differences in color seen in A and B, are representing changes in the dielectric constant.
Yeah. Yeah, and in this particular case, this is on the North Polar layer deposits, and you're basically seeing variations in the dust content of the ice.
I have a question if that one is concluded. And I'm not sure how much you know about this, but I'm curious what the utility of having a microphone on Perseverance is.
You're inviting me to make snarky scientist versus engineer comments. The utility is to do it. I think with a lot of NASA missions, there are some things that are done simply because they are cool and to prove that we can. I think this mission is maybe a little heavy on that, actually. There are a lot of things that are just to be neat, for the engineers to prove they can do it, and to get people in the public excited. Nobody ever heard the wind on Mars before, now we have.
Fair enough.
It seems like the more the public has an interest and awareness of what it is actually like on Mars, the easier it might be to convince future funding and actually provide the much more scientifically rigorous experiments.
Yeah, I mean, I think the critical science on this mission is coming out of the spectrometers. The visible imagers, though, they do a lot of public outreach too, and the radar. Then there's a lot of this whiz-bang stuff. The helicopter, I think, is very much whiz-bang. There will be benefits in planning the route, but it's not like they didn't plan rover routes before they had a helicopter. It's just to prove it could be done and to look cool.
Hannah, can you go back to your slide showing ice depth versus time?
I'm sorry, ice depth versus,
Time.
oh yeah. This one or one of the later ones?
This one, yeah. So this was simulated data, right?
Yes, so this is coming from, this is coming from a 1D atmospheric and subsurface temperature model that is informed by a lot of 3D atmospheric considerations.
Okay, I was just kind of wondering about what went into the model. It looks like obliquity figures in to a large extent with a lot of these landing sites, but looks like on Phoenix there's some shorter timescale oscillations. I was wondering what the main drivers for those were.
It looks like Hanna has frozen again momentarily. Hopefully she'll get back to us soon. In the meantime, if anyone else has any questions they wanted to ask before you need to sign off in a few minutes, feel free to put them in the chat and we can, if we have a little bit of extra time, talk about them. All right, looks like we lost her connection again. Hopefully she'll be able to get back to us in a moment.
I'm back now, so I'm assuming she's logging back in.
Okay.
My apologies. I know it's not my fault, but I'm the I'm Hannah's de facto unpaid tech support. So every time this happens, I feel like it's my fault.
All right, looks like we got Hannah. All right, so you're still muted, Hannah, but if you got the question before we lost you.
Yeah, I'll try to answer it verbally quickly and then get the plot back up. But basically, Walter was asking about the kind of like higher frequency variation in the depth of the ice at the Phoenix site that's not, doesn't seem to be correlated with the obliquity. So obliquity is only one thing that's affecting, the solar ephemeris and the thermal history, also the eccentricity of the orbit and the LS of perihelion, the aerocentric longitude of the sun at perihelion. And so those higher order wobbles are coming from those. We just didn't put a panel in for them.
Thank you.
Would you say then that the obliquity is the more likely primary factor?
Yeah, it's dominant. Definitely for the last 10 million years, it's dominant. And we actually ran this stuff back farther. There's kind of like a large scale envelope to the obliquity oscillation that has a longer phase. And so 5 million years ago, most of the models predict that we kind of moved to this higher obliquity phase in general. So a big thing that Perseverance can do for us is if we actually get there and we see a lot of ice, then we'll be like, oh, that really happened. We really were in that persistent high obliquity phase several million years ago. Right now, I'd say a lot of us are skeptical.
Here's hoping for that future knowledge.
Well, it's not as simple as I just made it sound, but it would be a very exciting climate result that could do a lot for validating and improving models if we did find something there. I expect we're going to find a lot of dry rock.
Good to keep your hopes in check. So it is 1 o'clock right now. I understand if people do need to leave, but Hannah, if you are open to sticking around a little bit, if we do still have more questions from the audience, please ask away. Otherwise, as always, these talks are recorded and put onto our YouTube channel, so you can always check out the rest of the talk you may have missed once we've uploaded it.
I expected to have Dennis Egan here asking me a lot of questions.
Well, I'm sure he can always get in touch with you if he manages to watch things. But it looks like if there are no more questions, then we'll wrap things up here. Thank you again, Hannah. It's absolutely a blast getting to hear from you and getting to learn a little bit more about the actual science going on in Perseverance and in general on Mars in the future.
Thanks for the invitation and nice to meet you, Jesse. Hopefully in person soon.
Agreed, yes. So I look forward to meeting you in person, and for everyone else, next week we will have a speaker, again, long time in the works, University of Pennsylvania, Jeff Luniano. So everyone take care, and hope to see you again next week.